So next talk from Merve Sahin is titled AI for Vulnerability Detection and Repair, Opportunities and Challenges. Merve is a security researcher at SAP company, and the floor is yours.
Thank you so much. Yeah, so hi everyone. My name is Merve Sahin. I am working in the product security team of SAP. And today actually the previous talk was a great introduction. I will also talk about using AI for vulnerability detection, but also for repair. And on the repair part, actually, I will present a study that we did recently together with the Technical University of Braunschweig. We had basically Kendrick, who did his master's thesis with us, with SAP and TU Braunschweig. And we also had Malte Wessels from TU Braunschweig, who is currently about to finish his PhD. Yeah, so let's start. So I guess you all have heard about the news last month about the AI vulnerability storm. So now we have these very powerful LLMs that are combined with, again, very powerful AI coding, agentic coding frameworks or harnesses. And they're able to find very a lot of 0 days in very critical software, so we have been seeing lots of news recently. And basically, the current recommendation for the CISOs or for software companies is to immediately start by asking a coding agent for a security review of any code you have, which is indeed a great recommendation because we know that the AI is very good at vulnerability detection. This talk I will focus on static detection, unlike the previous one, which was about dynamic testing. So traditionally, we call it in short SAST, so static application security testing. It's really widely used in industry because it scales very well. I guess you know some of these companies that are like SaaS vendors. But recently what we're observing is that the LLMs are actually able to find vulnerabilities that traditional SaaS tools are unable to find usually, such as the logic flows like we discussed, weaknesses in input sanitization, validation functions, interactions, flows between components, and so on. Moreover, the LLMs have extensive knowledge of the frameworks or technologies that you use in the code, so they can really identify the risky configurations or weak code patterns and they can tell you, okay, now you don't have a vulnerability, but if you refactor the code in the future, you might have this sort of an issue. So it's quite useful to do static code review with LLMs and coding agents. But of course, there's the other side of the story, like what can go wrong. We need to be aware of the potential issues, especially if we want to use this at scale, running it on hundreds of thousands of repositories. So the first challenge is, of course, false positives that comes inherently with static analysis. But in the case of AI coding agents, it's a bit maybe more tricky because it will always give you some plausible explanations of why the code is vulnerable. So it might actually require a higher security expertise to audit or verify the finding. There are strategies to reduce the false positives, even if you only do static analysis. I won't go into details, but this is a really great blog post that gives some methods, explains some ways to reduce false positives. Another challenge is the non-determinism, of course. The studies show that LLMs can give basically inconsistent findings. So if you ask the first 4 times, it says, yes, the code is vulnerable. The 5th time, it says, no, it's not. Also, it might give inconsistent severity ratings, and sometimes even if the vulnerability type is correctly detected, the reasoning might be wrong. Of course, this makes it very difficult to track and document the vulnerabilities, which we usually require for compliance and auditing reasons. Another challenge is potential user-induced bias, because the LLMs are instruction-tuned. They tend to follow users' assumptions, so if the human or the developer is having a wrong assumption or giving incorrect input, the LLM may get convinced that it's not a vulnerability. And finally, there are many cases that we observe that the analysis may lack a systematic coverage of the code base and systematic coverage of the vulnerability types. For instance, sometimes when you ask the agent to detect vulnerabilities, it finds one representative example per category instead of being exhaustive, or there are also cases that you see it does not actually cover all the code base, even if it was told so. Yeah, so there are several challenges. Just as a small summary, it's indeed essential to start using AI for vulnerability detection. It's becoming a standard practice, but currently, like converting an AI coding agent into really robust, reliable security tooling is difficult. Also for static analysis, it's not very clear what works best. So do we still need the traditional SAS tools? Should we do it only AI-based, or should we combine the two in a certain way? In which way? So these are open questions. So coming to the second part. So historically, vulnerability repair has been the least automated step, because for the detection, we have a lot of tooling available, but the repair is usually done by the developer, who hopefully has security expertise and will understand the issue and fix it correctly. But of course, with the rise of LLMs, now we have many security vendors and also AI vendors that are advertising these AI-generated vulnerability features. But of course, these also come with a certain cost, so we want to understand what is the actual potential of LLMs to fix vulnerabilities. Actually, there is a very large volume of academic literature on this, but most of the studies focus on function level fixes, so the vulnerability lies only in one function. Also, most of the studies focus on C++ or Java languages. And the results they report are mixed, so we see vulnerability correct, successful fix rates from 10% to 90% reported, depending on the technique, the model, the data set that was used, etc. So in our study, we did something a bit different than the existing work. First, we focused on web languages like PHP and JavaScript. Second, we focused on file level repair, which is a bit more advanced than function level. We used the real world data set, and we evaluated 17 different LLMs. That was state of the art at the time we did the experiments, which was last year. So now it's a bit outdated, of course, but you can see the results as the lower bound. And yeah, so to evaluate the fixes, we used 7 different state-of-the-art SAS tools, and sometimes the unit tests as well. So for the dataset, we use the CV fixes dataset, which is commonly used in academia. This dataset contains more than 11,000 vulnerability reports, and we have both the vulnerable and fixed code available. So we did lots of filtering on this, and also a lot of human verification, manual analysis, and SAS scans. So finally, we ended up with 75 code pairs where we know that there's at least one SAS tool that can detect the exact vulnerability that was reported in the CVE. So before going into how LLMs can fix vulnerabilities, let's check how humans can first. So we manually analyzed the human fixes from the data set, and we actually found that 11% of it were incomplete, in the sense that, for instance, they were not analyzing, validating, or sanitizing all sensitive inputs possible. In 33% of the cases, the vulnerability fix had some design flaws, such as not using well-established security practices or libraries. And we even found one case where the fix actually introduced a different type of vulnerability. So coming back to the LLM fixes, so we know that each vulnerable code file corresponds to a SAS finding. So to generate the fix, we basically prompted the LLM with the vulnerable code file that is annotated with the SAST finding. So in the vulnerable data flow that is reported from the SAST finding, we see at each line where is the data flow we show. Then we ask the LLM to generate the fix. We get the fix, but then there is the other tricky point that how do we evaluate if the fix is correct or not in an automated way. It's actually quite hard to automate this task. So it's not perfect, but we did the best effort. So in most cases, we relied on the SAST scan again. We scanned the code again and check if the SAST finding is disappearing or not. And in some cases where this was not looking very reliable, we actually manually wrote unit tests to see if the fix is still functional and not vulnerable. Here are the prompt templates we used. So in the zero-shot prompting case, as I said, we give the vulnerable code with the SAST annotations. And we asked the LLM basically to return the fixed version in the file in its entirety, do not perform any other changes other than the fix, etc. We also wanted to experiment with the few-shot prompting. So basically for some of the language and vulnerability type pairs, we had a few-shot prompt templates where we first, for example, give some explanation about the vulnerability type, and then we give examples of vulnerable and fixed code to help the LLM understand what to do better. This is an overview of the results. So as you see, the best performing models, they achieved around 85-86% of success rate in successfully fixing vulnerability. One thing to notice here is that actually for models, larger models with a lot of parameters, few-shot prompting does not really help. Actually, zero-shot prompting works better, but for smaller models, few-shot examples were actually helping them to improve. Just a quick analysis of the LLM fixes. So in the cases that it fails, we realize that it's because the LLM generates either too much text, attempts to make too many changes, and sometimes it was only refactoring code without fixing the vulnerability. But in the successful cases, the LLM fix was more complete, better designed than human fix, also more structured, like instead of doing a single line fix like humans try to do most of the time, it was using helper functions and so on. And in general, the LLM fix was longer in length in the lines of code than compared to the human fix. This is an example where the LLM fix works better than the human one. So here, this is an SQL injection vulnerability. The human fix uses a method basically to escape certain special characters, but actually this method is bypassable in certain cases. It does not escape all possible characters. But in the LLM fix, it was the correct way of doing it, so it was actually using prepared statements to prevent the vulnerability. Of course, one question that comes to mind is because we have the CV data set, which is mostly overlapping with the training data of the LLMs. So did the LLMs just memorize the human fixes? So we also looked into this, and we found very little evidence showing that. So only in 1% of the cases there was an exact match between the human and LLM fix. And these were trivial fixes that anyway does not have too many ways to do. And only in 5% of the cases we saw that the LLM is replicating the abstract syntax tree of the human fix. So overall we can say that the LLMs are actually generalizing the repair patterns rather than just reproducing what is in the training data. Also, we did a small experiment, the small data set, but we checked the success rate for the LLM fix for the cases that is not, when the CV is not in the training data. again, it's not a big data set, but we saw that the success rates are comparable, like 74% for previously unseen CVEs compared to 82% for the CVEs that are known before. Okay, so in conclusion, we can say that AI agents can largely automate vulnerability detection and repair tasks, but it's still a challenge to engineer reliable and scalable security solutions with them. And whatever method we come up with, it should also evolve because the models are evolving, so it's like a never-ending story. Currently, the software security landscape is also changing a lot, so we have the traditional vendors trying to adopt, integrate AI. We have the AI native startups. We have the AI companies entering into security field, like cloud security, codex security, and so on. And there's a big race on who will build the most security capable model, who will design the most effective harness, who will combine the AI with traditional tooling in the most efficient way, and how are we going to integrate this to the developer workflow in a seamless way. So thank you so much, and if you have any experiences, I would be happy to hear.
Thank you. So we are a little late, so one or two questions max. Mark?
Thank you, Merve. I have a meta question. So in software companies, it is well known that the cost of the software is not so much the cost of the development, but the cost of ownership. And there are decades of work that have shown that if you look at the lifetime of a big software, at first the amount of bugs you fix per period of time goes down, which is normal, but then there is a moment where it goes up again because the code is less readable, the people have changed, and so on and so forth. If we go on with AI now to do this fixing, do you think we will have the same problem faster because AI will touch, but the model of the AI will touch, so maybe one day it will decide to change it for this, and then maybe like this, and or is it, at the contrary, getting better? We will not have that problem anymore.
Yeah, it's a very good question. What happens like when we really give all this auto fix, automated repair thing to the developers? Honestly, I don't really know the question. Currently, the hope is that, of course, it's still the developer's responsibility to know what is going on in the code, to check if the fix, to understand the fix. Yeah, I don't know the answer of your question in the long term when this gets big at scale. Good point.
Hello, thank you. Oh, sorry, first.
Thank you very much for the talk. It's good to see AI not only for detection of vulnerabilities, but also fixing the issues. I was wondering, how do you define when you need to add a security check that the fix is okay? And how do you think that it's okay to rely on rerunning the SAST analysis?
Yeah, that's definitely a limitation of, actually I have a slide on the limitations. Yeah, definitely, so we rely on the SAST tool, but then we don't really know if the functionality is still there or not. As I said, it's very difficult to automate because for certain of those cases, we indeed wrote unit tests to check for both functionality and security, like if the payload still works or not, if it is vulnerable or not. But in general, automatically checking if a certain code is vulnerable and functionality is there, it's very difficult. So this is a limitation of the study. It's indeed the best effort.
Okay. Last one.
Hello, thank you for your presentation. I just want to talk about the discussion I've got with a company which use cloud to validate the code before going in production. And they say we really see the age of the training of cloud because they sometimes just completely suggest very old-fashioned way, or using very compromised libraries. And so it's really problematic for them. They just switch off cloud recently because they were losing too many times time about trying to explain to Claude, no, we want the most recent version, and every time it says, but it's not out there. It's a program for 2025.
Yeah, actually, about that, so I mean, in this talk, I didn't talk about the open dependencies, vulnerable dependencies, etc., that the AI agent might introduce. But there are some solutions on that. For example, for I think it's called the Context 7. It's the MCP server that basically can tell the AI agent, because the LLM will not know about the recent status of all open source components, the latest versions. So there are ways to embed this information afterwards, actually.
Sorry, thank you.
Thank you very much.
Thanks again. Next speaker, please.